Okay, in this video, we're going to introduce a key idea of basic solutions and basic feasible solutions. But before we get to that, let's introduce the sort of matrix vector way of writing an optimization problem. Okay, so here is a linear program, a maximization problem in augmented format. And essentially, let's break down what each of the parts of this are. So the X vector, and I use boldface when I'm writing it in LaTeX or kind of making it, typing it up. But I guess when I'm writing it out by hand, I often put a little arrow over top. So X is a vector. It is, well, we'll do it for the case of the Geppetto problem. It's essentially a vector of all of our variables. And so it's our variable vector. And then in the case of Geppetto's problem, it's X soldiers and X trains. Okay, and then we've also got an S vector. That's our vector of slack variables. And so that would be the slack for finishing, slack for carpentry, and slack for demand. Okay, and often we'll sort of combine these two into one super vector, and I'll do that in just a bit. Okay, and so that covers the X and the S. The C, that's going to be the coefficients of X, S, and XT in the objective function. Okay, and so if we think about our objective for Geppetto's problem, there's a 3 is the coefficient of X, S, and 2 is the coefficient of XT. And so C, and I'll kind of write it as a transpose, so we think of it as a row vector, is the vector 3, 2. And so you can think of that as our objective coefficients. Okay. Our A is going to be a matrix. It's our constraint matrix. It's the coefficients of X, S, and XT in the constraints. And so if I look here and look back here, the coefficients of XS and ST are going to be what form the coefficients of the A matrix. In this case, our A matrix would be, for the first constraint, we've got 2 and 1 are the coefficients of X, S, and XT. And then we've got 1 and 1 and 1 and 0. And so we could represent those same inequalities or constraints as a matrix vector product of this A matrix multiplied by this X vector. And so looking at this line here essentially summarizes the constraints in augmented format. So we do A times the X vector plus the slack variables equals the right-hand side. And so maybe I'll call this the constraint matrix. And then I'm maybe running out of room, so I'm going to come back over here. The B vector is going to be the right-hand side, and that's essentially going to capture the right-hand sides of these constraints, or maybe actually looking at an augmented format, it's the same right-hand sides. Okay, but now we've got equalities, which is what we've got in this setup where we've got equalities here. And so the right-hand sides are then 100, 80, 40. And so this gives us a compact way of maybe writing a general linear program. And if you think about it, what's the things that are going to change are really how many variables do we have, how many constraints do we have, how many slack variables then do we have, what are the coefficients in the constraint matrix, what are the coefficients of the objective, what are the right-hand sides. Okay, and so this is sort of the LP in general, but then once we specify each of these things, we've sort of specified a specific linear program. Nice thing is that we can kind of talk in generalities, and then the general process applies to each of the specific problems that we see in the future. Okay, so the A matrix is going to be an M by N matrix. M is the number of rows in the matrix, which is the number of constraints. So this is the number of constraints. And n is going to be the number of columns in the matrix, and the number of columns corresponds to the number of variables. Okay, so in this case, for Geppetto's problem, there's 3 constraints and 2 variables. So this A matrix is a 3x2. Different problems will get different shapes. Okay, so a basic solution happens when we choose n, where n is the number of variables. We choose n of them to be 0 and m of them to be non-zero. Okay, and that's the combined entries of both x and s. So we sort of pool x and s into one combined vector, and then think about the variable, and then we want n of them to be 0 and m of them to be non-zero. Okay. It's a basic feasible solution provided that it satisfies all the constraints of the LP. And if we remember from the previous examples, once we've turned it into augmented format, the only thing we need to do to check whether it satisfies the constraints is check non-negativity on the slack variables and the original variables. So all we got to do is ask, are they not negative? And if they're all not negative, then we're good to go. Okay. So maybe I'll actually let's take these matrices and let's actually put this into an augmented matrix and think about what this line here really looks like, or really take this set of equations and turn it into a matrix vector system, similar to the matrix vector systems that we talked about last week. I'll kind of pull it up over here. So first in here, we're going to essentially think about this matrix as then we're going to combine our 2 vectors together. So we're going to have x, s, x, t, but then we're also going to combine our slack variables in here. So slack f, slack c, and slack d equals our right-hand side. Okay, and so for the first constraint, we've got 2xs, 1xt, 1xsf. So that's, and what I often find easier is if we think about the first row multiplied by this column, it helps to kind of label up here xs, xt, sf, sc, and sd. To label over the columns, because we can really think of each column as corresponding to one of those variables. And so the coefficients are 2, 1, 1, and then SC and SD don't show up in the first constraint, and so they both have zeros, and then that should be equal to, on the right-hand side, the value of 100. Let's do it for the next row here, which is going to be this constraint in augmented form. And so that's going to be 1xs, 1xt, no SF, 1sc, no SD. And the last one is going to be 1, 0, and then 0, 0, 1. Okay, because that last constraint involves just 1 times xs plus 1 times SD. All the other variables don't show up. And so that's the same as having 0 for their coefficients. Okay, and those should be equal to 80 and 40. Okay, so this is essentially our constraints, inequality form for because we're an augmented form. And if we find a solution to this system that has, in this case, we want 2 of them to be 0 and 3 of them to be non-zero, then that's going to be what we call a basic solution. Okay. The key idea of why we're interested in these basic solutions is that basic solutions happen when constraints intersect. And it's when exactly n of the constraints intersect. some of these are outside of the feasible region, and that's where you'll get non-feasible basic solutions. And some of these are inside or on the actual boundary of the feasible region. And those ones are going to be our corner points. And if we're kind of thinking about solving linear programs, we said last week that the corner points are where those optimal solutions are. Okay, so let's actually find all the basic solutions for Geppetto's problem and note which are feasible. Okay, we're going to take advantage of geometry for this. We'll talk a little bit in the next video on how you'd find this if you didn't have a nice picture to go off. But essentially, each of our basic solutions are going to happen when two constraints intersect. And by constraints, I'm thinking my functional constraints, but I'm also thinking of my non-negativity constraints. And so I've actually labeled each of the basic solutions here in their xs and xt coordinates. So 0, 0 is the intersection of my two non-negativity constraints. The kind of the two axes are actually constraints as well. 40, 0 is a basic solution. 50, 0, 80, 0, 40, 40, 20, 60, 0, 80. So let's kind of write down what each of those are. So I'll write down the first one. So 0, 0, and let's and that's in sort of coordinates of x, s, x, t. Let's go ahead and figure out what's the full augmented vector for that, including the slack variables. And so essentially, here's the trick. I can plug in values of xs and xt into this and solve for the slack variables. Okay, and that's exactly what we were doing a couple videos ago when we were doing this. Okay, so plugging them in, if I plug in 0 for xs and 0 for xt, that essentially removes these two columns because they're going to be multiplied by 0. And then this first row, if I sort of hide these two columns, I'll get 1 times SF plus 0 times SC plus 0 times SD, or just SF equals 100. And so this is kind of the nice case. So X, S, X, T, S, F, S, C, and S, D. So I can read off essentially, because I've got 1 here, 0, 0 here, that SF is equal to 100. So if I make no soldiers and trains, I've got 100 hours of finishing slack because I haven't made anything, and I had 100 hours of finishing labor to begin with. Similarly, if I hide these two columns and I'm looking at SC, or this next row, it just says, the left side just says SC equals 80. And then the last row just says SD equals 40. And so at the origin, or at 0, 0 in this picture, I've got 100 units of finishing slack, I've got 80 units of carpentry slack, and I've got 40 extra units of demand for soldiers. And so this is a basic solution. 2 of them are 0, 3 of them are non-zero, okay, which matches up what we said as far as the correct number of non-zeros. And is it feasible? Now to check, is it feasible? All we need to check is, are there any negatives? In this case, no negatives, so yes, it's feasible. Okay, that was maybe an easy one. Let's do the next one, or a next one. So let's look at 40, 0. Okay, I'm going to plug in 40 here, 0 here. Okay, and I'm going to use a little bit of help from geometry as well. So at 40, 0, which constraint has no slack, or which of the other constraints has no slack? Well, at 40, 0, we're on this demand constraint, and so there's no slack for the demand variable. And so then I know that SD, slack for demand, is equal to 0. Okay, that leaves me left finding only SF and SC. And I guess I've already solved for XS at that point. But you could solve for it just knowing that these two are now 0. So let me pull up an extra piece of scratch paper to do this one on. And so I'll look at each of those constraints. And so the first constraint for finishing, I'll have 2 times XS, 2 times 40, plus 0, which is XT, plus my slack for finishing equals 100. So 2 times 40 is 80. I'll subtract 80 from both sides. And so that gives me SF equals 20. So I've got 20 extra finishing hours of labor. If I look at carpentry, I've got 40 and 0 plus S carpentry equals 80. And subtracting 40 from both sides gives me that SC equals 40. Okay, 2 zeros, 3 non-zeros. We know that it's on the intersection of constraints. There are no negatives in this vector, so yes, it's feasible. Okay. Next up, we'll do 50, 0. Okay, notice I didn't have to check the demand one because I already knew that there was no slack for demand. Okay. So at 50, 0, now let's do finishing again. And let's see, that is 2 times 50 plus 0 plus SF equals 100. And that gives us 2 times 50 is 100, subtract 100 from both sides, gives us that there is no slack in the finishing constraint, which is what we'd expect if we'd looked at this diagram. 50, 0 is exactly on the finishing boundary for that constraint. So 0 for finishing. If I look at carpentry, that is 50 plus 0 plus S carpentry equals 80. Subtracting 50 from both sides, S carpentry equals 30. Whoops, I meant to write 0 up there. So these are for 40, 0. These are for 50, 0. Okay. And then finally, let's actually look at demand, because we're not on the demand constraint. And so I know I have a non-zero amount of demand, or I have a non-zero amount of slack. So here I've got 50 for soldiers plus S demand equals 40. Now, if I subtract 50 from both sides, I get that the slack in the demand is -10, meaning that we've gone over our demand for soldiers. We've made 50 when we said that we could only make 40. And so we've got a negative amount of slack, which means we were on the wrong side of that, of the original constraint for demand. So filling in those values up here, we got 30 and -10. And is that feasible? No. And that's because we got a negative value for one of the variables. And so not a feasible, basic feasible solution. Okay. I'm gonna write out the rest of them, and then I want you to kind of pause the video and try the same process to find what's the rest of the slack variables essentially, and yeah, is it a feasible basic feasible solution? Okay, here are the rest of the points that are corner points of Geppetto's problem. And so these are all going to be basic solutions. Some of these are going to be feasible. Some of these are going to be not feasible. Go ahead and use the equality form of the constraints to solve for the missing slack variables, and then determine which of these are feasible or not feasible. Pause the video, work it out. I'll show you the answers in just a moment. Okay, here you go. Here are the kind of full augmented vectors for each of the rest of them. We see that all the ones that have negatives in those augmented vectors are the ones that are not feasible. All the rest are basic feasible solutions. Okay, and this idea of basic feasible solutions corresponds to corner points in here. And so the corner points that are actually on the boundary of the feasible region are the ones that are feasible. Those are the BFSs. The ones that correspond to intersections that are beyond here, like up here, this corner here, or this 40-40, or this 80-20, they're intersections of two constraints. But they're sort of outside of the feasible region. So that's it for this video, introducing the idea of basic solutions and basic feasible solutions.